Well, hello everybody. Let me show you what we got going on today. Sorry I'm not there to be able to help you out on any questions that you might have, but if you do have some questions, get in and we'll sure get you straightened out on those. What I need to go over with you today is I need to talk about the number e a little bit. Should be reviewed from your Algebra 2 days, and then the natural logarithms, which is the inverse of the number e. So I really think a lot of this will look familiar from your Algebra 2 days, but we shall see. Where I'd like to start there, though, flip over to your class examples where we have that compounding schedule. I won't go through all of this, but I do want to show you where the number e is derived from. The number e assumes this. You can pick any amount that you'd like to invest, but the interest rate won't change. What the number e, where it comes from, it goes like this. It says, assume that you invest $1 annually at 100% interest. How much money would be there after 1 year? And then what we're going to do is look at the various compoundings. What if I compounded it yearly, semi-annually, monthly, daily, hourly, every second, as fast as we could? And then we arrive at a number that's used to represent continuous change, and you already know where that number is going to be. It's going to be our number e. So hang with me for just a little bit right here on this compounding schedule. Here's what I'm going to do. Under compoundings, I'm going to assume that we compound something annually, quarterly, monthly, daily, hourly. So what I did, guys, the number of days, 365 times the number of hours. So let's go 365 times 24 hours in a day. So let's go 8,760 hours in a year. If we want to get a little fancy, I could turn that into minutes by multiplying by 60. But let's even go further. Let's go ahead and multiply that by 60 again to get the number of seconds in a year. Like I said, we won't take time to run all of these numbers through in a video, but here's the number that we're going to start looking at. After I do a couple, you'll understand what I'm typing in. So here goes. I'm going to assume I put in $1. I'm going to assume my 1 plus. I'm going to assume my rate is 100%, so I'm going to use a 1 over 1 compounding to the 1. Well, if you run that through your calculator, this 1 out front's really not going to matter. 1 plus 1 is 2. 2 to the first is 2. Let's see what quarterly would look like. Like I said, the 1 out front really doesn't matter, but I'm going to have a 1 plus 1 over 4 compounded 4 times. Well, if we come over here and run that through our calculator real fast, I got 1 plus 1 divided by 4. And let's raise that to the 4th power. Well, now notice that I got up to 2.4414. And that wrote terribly. Let me see if I can clean that up real fast. That's why I like using PowerPoint better than the Interwrite sometimes. So I've got approximately 2.441406. Really, we should list as many decimals as we can, but you'll quickly get the picture. If we look at monthly, I'm going to have a 1 plus 1 divided by 12 to the 12th. So let's go 1 plus 1 divided by 12 to the 12th. Kind of look at what that number happens to do. 2.613035. Let's hit it again. Let's go 1 plus 1 divided by 365. If we compound it every day, then you're going to get 365 compoundings in a year. Look at what that number is. So it's going to be approximately 2.714567. Notice that it's still growing, but not near as fast. Let's look at 1 plus 1 divided by 8760. Raised to the 8,760th power. Now I'm at 2.718 1266. And I can keep doing that as fast as I can. Where you'll see this used at is really in the sciences, in bacteria. But this just says if you can compound your money as fast as you could, if you can beat compounding it every second, then more power to you. So look at where this number is approaching. Notice that it's not growing near as fast. So if we keep playing that game, I could have went every second, then I could even win every half a second. We would have approached the number E. That number was, it's called the letter E because it's given to honor the mathematician Leonhard Euler, 1707 to 1783. What's kind of cool about that number, he did everything that I just did in my calculator. He did it all by hand to kind of see how far those decimals would go. And he would run them out to 13, 15, maybe even 20 places. So it's pretty impressive how a lot of these numbers were derived without a calculator that spoils you and I. So here's the number. You can get to that number on your calculator, guys. If you go second, right there above the natural log, there's the E. Raise that to the first power. Your calculator can get you to that number E. So we'll use that a little bit. You'll know to use this upcoming formula with the E in there whenever you hear the word continuous. So let's see if some of these look familiar to you. I'm going to throw some formulas at you. Remind me when we get back, and we'll put these on a note card. Or if I left note cards there with my sub, ask for a note card and then put them on today. But here's what we got. We got this model called the continuous change model, just aka PERT. If a quantity grows or decays continuously at an annual rate, the amount after t years is going to be given by a sub t equal principal to the number e raised to the RT, your interest rate as a decimal, times the time. A couple of other formulas that you're going to see today, then we'll kind of use them here in a second. You'll see what we call the annual yield formulas. What these formulas do is they ask you, let's say that you are paid 5% interest compounded quarterly. Well, what would that number be if you were paid annually with just one compounding? So we'll run some through here in a second, but if I'm paid 5% compounded quarterly, it might be something like 5.12% equivalent out annually. That's what these formulas get you to. Notice that it doesn't matter what the principal is, and then we assume time is 1 year, so that's why you don't see a T in there. So they're called the annual yield. We'll use them here in just a heartbeat. If you're looking for the annual yield and you're compounded quarterly or continuously, here's this formula here. So like I said, if we have a note card, we'll write those on there for you. If not, remind me next time, we'll put them on a note card. So if you will, look down at your example 1. We'll start punching some numbers through and show you how this works. Number 1 says, how much more money will you receive if you invest $8,000 at 7% for 5 years continuously rather than compounded monthly? Well, so here goes. Let's look at continuous first. I'm going to have the amount's going to be, I'm going to use the continuous change formula of the amount is PERT. Well, let's go get some numbers now. I'm going to have 8,000 as my principal. E to the, and I'm going to put this in parentheses. My interest rate is 7%, so 0.07, times the number of years, 5. Well, let's come over here and run that through. I'm going to have 8,000, parenthesis, well, I'm not going to type it that way. Let's type it in this way. 8,000, second, go get your E. And most calculators will put a parenthesis there for you. If yours doesn't, you'll need to type that in. So times 0.07 times 5. Once I run that through, the amount I'm going to get paid if it's continuously is going to be $11,352.54. What we're going to start doing, guys, when we talk about money, we're not going to use the approximately sign. Because if I go to a bank, I'm going to get an exact amount of money. In this case, I would get $11,352.54. So there's what I would get if it's compounded continuously. Now let's come over and look at what if it's compounded quarterly or monthly. So the amount that I'd get if it's compounded monthly, I'm going to have to use this formula here. So there's my principal times 1 plus, I need 0.07 divided by 12 raised to the power of, and I'm going to put that in parentheses, 12 times 5. Normally what I do is when I run this through, I do that part in my head just so it's easier to type in. But if you're going to let your calculator do all the work, we're going to go 8,000 times 1 plus 0.07 divided by 12. Let's raise that to parenthesis 12 times 5. And you know, we should get something in the ballpark of $11,352. In this case, it looks like the amount I'm going to get, $11,341, and looks like flat. Now, let's answer the question, though. It says, how much more money will you receive? Well, so what I need to do is I need to take that $11,352.54, subtract away 11,341. So to answer the question, we're going to get $11.54 more than if it was just compounded monthly. So there's that answer. Look down at example 2. It says compute the annual rates for both investments. Here you'll understand what I mean. Right now I'm getting 7%. But what would that be if we wanted to just talk in terms of annually? That's what most banks do. If you walk in, you won't see how they're going to compound your money. They won't tell you that, hey, we're giving you 1% interest compounded monthly. They're just going to tell you what it would be every year. So here goes. I'm going to do this one first. So I'm going to have e to the r minus 1. That's going to be my rate for continuous. So I'm going to have to go e to the 0.07 minus 1. Let me come type that in. So I've got my e to the 0.07. Let me get away from that, minus 1. So see if this makes sense. Compounding my money continuously at 7% is the exact same thing as earning about 7.251% annually. If I look at the other one, the one compounded monthly, it's going to look like this. I'm going to use my formula right there. So I'm going to have 1 plus my interest rate of 0.07 divided by 12 raised to the power of 12, whatever that answer is, minus 1. Well, you know, we better get something kind of close to 7. So I got 1 plus 0.07 divided by 12 raised to the 12th, whatever that answer is, minus 1. 0.07229. So that's going to be about, I need to backtrack and put in approximately on this because we are rounding. So I need to get about 7.229%. So there's how you use those effective rate formulas. Just kind of run them right through your calculator. You know you're going to get something in the ballpark of what your interest rate is. Okay. Click over to your example 3 if you would. It says, suppose $500 is invested in an account paying 8% annual interest rate. What's the balance in 4.5 years if the interest is compounded continuously? That's your cue to use this formula right there. So here goes. I'm going to have my amount's going to be the $500, my principal, e to the 0.08 times 4.5. 500, second e, 0.08 times 4.5. Looks like I'm going to get $716.66. The sad thing right now in today's market, there's nothing close to 8%, but we can do the math of it. Here goes part B. How does this balance compare with the quarterly compoundings over 4.5 years? So let's go use the other formula. So my amount's going to be 500. 1 plus 0.08 divided by 4 raised to the 4 times 4.5. I'll run this one through, and then most of them after this one, guys, I'm just going to write the answer. So I got 1 plus 0.08 divided by 4. Close that off, caret parenthesis. Don't forget that, otherwise it'll really mess your answer up. And my 4 times 4.5, close that off, and it looks like in this case I'm going to get $714.12. Now let's make sure we answer the question. It says, how does it compare with the quarterly compoundings? I'm going to say that continuously I'm going to get $2.54 more. On to example 4. These are just some things I wanted to make sure that you could type into your calculator. I really won't spend much time here. If we want to evaluate e to the 1.64, you can probably guess what I'm going to do there. There's e to the 1.64. Run that through, round to 4 decimal places, so I'm going to have approximately 5.1552. If I want to do the natural log of 0.5, that's as easy as you think. The natural log of 0.45, I'm going to have approximately negative 0.7985. Now this one we're going to use off and on here, so let me go ahead and go the natural log of e. Let me hit that correctly too. Let's go the natural log of e. Watch what happens on this. This is really important because the natural log and e are inverses of each other. Whenever they're inverses of each other, they're going to wind up canceling each other out. The reason that happens is it happens here. Whenever you see the natural log, the base right here is an e. So it's really asking this question. What can I take the natural log of and get the e? So it's saying e to the what will give me e. Well, that what has to be a 1. The other little one that I'm just looking at over here, e to the 0, that's going to be 1. Anything to the 0 is 1. The natural log of 1, we could type that into our calculator, but it's going to be 0. The reason being, it says e to the what power is going to give you a 1. Well, anything to the 0 is going to give me the 1. So if you will, flip over to your example 5, and we're not far from done on my class examples. Need to show you what some graphs of them look like though. And we're going to graph these by hand because I think you'll see it better. What I'd like to do first is graph y equal 2 to the x. And I'm going to do that by just setting up an XY chart. And we're going to graph this in our head. So I'm going to let x be 0, at n1, at n2, and 3, and then I may come back and get some more points. We'll see. 2 to the 0 is 1. 2 to the first is 2. 2 squared is 4. 2 cubed is 8. While I'm here then, let's look at negative 1 and negative 2. 2 to the negative 1 is the same thing as 1 over 2 to the first. That's our day 0 video stuff. So that's going to be 1/2 and 1/4. I do want to point out real fast, even if I use negative 10, guys, that's going to be 1 over 2 to the 10th, which is still some positive number. So this part will never ever be negative. It will never ever dip below the x-axis then, or the x-axis. So let's graph it real fast. I've got 0, 1. I've got 1, 2. I've got 2, 4. I've got 3, 8. I've got negative 1, 1/2. I've got negative 2, 1/4. So here's the graph of 2 to the x. Here in a second, we'll talk about the domain and the range of these. Okay. Well, now let's come back and graph y equal log to the base 2 of x. I'll show you how to type this into your calculator here sometime soon. It's called the change of base formula. But for today, I'm going to think of this as 2 to the y equal x. Base exponent answer. Well, check out what happens on this. What I'm going to do now is I'm going to pick some numbers for y and go get them. I'm going to let y be 0, and then 1, and 2, and 3, -1, and -2. Well, watch what happens. 2 to the 0 is 1. 2 to the first is 2. 2 squared is 4. 2 cubed is 8. 2 to the -1 is 1/2. 2 to the -2 is 1/4. Notice these numbers, 0, 1, 1, 0, 1, 2, 2, 1. They look like inverses of each other. Remember, on inverses, guys, you just switch the x and the y. Well, let's look at what this graph looks like, though. I've got the point 1, 0. I've got the point 2, 1. I've got the point 4, 2. I've got 8, 3. I've also got 1/2 -1. I've got 1/4 -2. Same as earlier, though. I can never ever get a negative number over here. So now when I graph this, it's going to look like this. So there's that graph. Looks like mine crosses over the y-axis. It doesn't. The x-axis acts as an asymptote for that, for one of them. The x-axis is an asymptote for the first one. The y-axis is an asymptote for my second one. So how are these graphs related to each other? They're inverses. If you also remember in our study of inverses, they're going to be a reflection over the line y equal x. Here on the next one, we'll sketch a couple of graphs. I'll show you how to type them into your calculator even. And we'll sketch it, and then we'll just quickly talk about them. So I'm almost done, to be truthful, guys. Come over to your example number 6. I won't plot the points this time. Let's come into your calculator, and let's go ahead and graph 5 to the x. Zoom 6 your calculator if you need. Keep in mind this, though. My main point on there, when x is 0, I'm still going to get 1. So I know this goes through the point 0, 1. So here's the graph of y equal 5 to the x. Let's talk about the domain and range of that real fast. The domain of it, -infinity to infinity. The range of it, 0 to infinity. Notice I did not include 0. The inverse of this, I need to write this in logarithmic form, so my inverse is going to be log to the base 5 of x. Log to the base 5 of x. Different calculators graph this function differently. I will show you a catch-all way to always be able to get it. To graph this, I'm going to use what's called the change of base formula. I'm going to think of this as log of x divided by, in this case, log of 5. So that's how we'll type it in. Let me come back and graph it. Notice that it happened to be right through here. Some key points on there, though. I know at 0, I know at 1, I'm going to get 0. So I'm going to go through this point right there, and this graph's going to look like that. A rough sketch is all we need, because I want to use that to answer the domain of the inverse. Well, the domain of the inverse looks like 0 to infinity. The range of the inverse, -infinity to infinity. And if you remember our study of the inverses, the domain of this should be the range of the other. The range of this should be the domain of that. So they match up. I've got one more coming your way, and I'm going to quit for the day. Here's your number 7. Given that f of x equal log to the base 7 of x. If you already know what the graph looks like, then just sketch it. If you don't, let's come back in. I'm going to think of this as log of x divided by log of 5. I mean, in this case, log of 7, man. So there's that. Would you like to guess the magical point that it went through again? And I'm hoping you said 1, 0. So there's that logarithmic graph. Its domain, 0 to infinity. Its range, negative infinity to infinity. The inverse of this, I'm going to put it in exponential form then. Normally it would be 7 to the y equal x. 7 to the y equal x. Switch your x and the y, so y is going to be 7 to the x. I know that that's going to go through the point 0, 1 and look something like this. So it looks like the domain of that, negative infinity to infinity. And it looks like the range is going to be 0 to infinity. I'm just going to come in here, put in my dotted line so you can see the inverse. Well, guys, that is really all there is to section 9-4. So your homework will use those formulas, and it'll review some logarithmic, and then we would have stuck, if I remember right, a little bit of, well, I thought we stuck some trig on there, but it doesn't look like we did. A little bit of that mixed review from our first day, because we struggled with some of those, so I'd like to get you better with those. So good luck on that, and come see me if you need any help.